to do a steep job like of appearance, so walking up the steps. So my name is Francisco Skembre, and I take full responsibility for what I'm going to say today, but this work would not have been possible without the cooperation with Felix Garcia, who's sitting right there, Walker and Christian, who's also sitting right there, and Mario Vilone, who's sitting somewhere in the United States. But first of all, let me dress properly. My father insists that one should wear a tie in special occasions like this one. So when I was about 17, 18 years old, he taught me how to tie my tie. I shall never forget that day. No, they don't. I want them to see how I tie my tie. But let's this one. Yeah. After you. So I was saying that I shall never forget that day. We were both standing side by side in front of the mirror. I was 18 years old, and he was doing the gestures, and I would be following, right? So this was the tie he used to do. And I was looking at him with kind of, well, admiration and paying attention to all the tricks. But I was able to do the tie properly. And this is what I learned when I was 17. And I have always, and I have always tied my tie the same way, without even questioning why, for more than 30 years. But 3 months ago, I was playing with my tablet in front of the television, and I saw an 18-second video that changed my life. That was the video. The video, this is a bazaar salesman in Istanbul, I don't know. And this is the way he tied. He was teaching an American tourist, a Spanish tourist, how to tie your tie. Here it goes. All right, so I don't know what happened, but it changed my life whenever I had to tie my tie. So, but I don't know what happened, but wow, I had to rush, jump from the sofa, rush to my room, grab a tie, and watch this video over and over, and learn the trick again, because I wanted to do that. And when I was doing it, I broke down for you. I noticed a few things. First, it was left-handed, right? And then, the second thing I noticed is that you don't need to take your hand closer to your neck. Only at the beginning, you cut your speed, and closer. And here it goes, right? So this is the tie I'm going to use today. And you're a wonderful audience. But I also went from then on, I also noticed a few things. I started wondering why this tie was different. Why I started the other way around with the short part on this side instead of the other. And now from then on, whenever I look at the tie, I wonder about the topology, well, not that much. But I wonder whether this knot would be better than the one I was using so for 30 years, or the one I just learned. No, I didn't lose my mind. I still remember this is not a fashion conference, but a physics teaching conference. So this story helps me bring focus to the keyword in teaching. For me, the keyword in teaching is motivation. What pulls from me to jump from the sofa and run to try to learn this? What was the motivation for me from doing that? If I was able to learn from this experience and learn how to motivate my students to learn physics, I would be a better teacher. So this is what I'm going to talk today, partially. So this is the table of contents, the structure of my talk today. I will spend some minutes giving you some reflections of how to motivate students. The second part of the talk, I will tell you my experience in trying to motivate math students, which is what I teach, to learn some more physics or to use the physics they learn by creating computer simulations. And finally, that will lead us naturally to talk about the tools that you need to do that. And our experience might be useful for you because we are a unique, I'm glad to be in a unique team where we have programmers, we have teachers, we have experienced physicists, and we can create our own tools. So you're going to see the tools that someone who needs it and can do it creates for himself. And I hope that will make it interesting. So let's go to the first of our part of it. So how to motivate young students? The key word is young, right? While there are a generation behind me, so I gave up. I don't know what students like or don't like. So the first thing I try to go is to ask for some help. And first I did it from the student's point of view. Suppose that you're a young student, you want to motivate yourself. So you Google for how to motivate a student. And what you get is a very nice number of pictures in a site called Pinterest, Pictures of Pinterest, which I didn't even know it existed. And I have selected a few of them. This is how they think they motivate themselves. Well, the first two, I'm not going to make a big deal of each of them, but the first one reads, what we learn becomes a part of who we are. That's not bad. But you could say the thing like, what we drink becomes a part of who you are. So, well, it gives you a hint, but it doesn't give me practical guide, practical ideas that I can use in my teaching. These two in the corners make reference to work hard, no matter how painful it is, eventually you'll do it. That one on the bottom reads, the harder the hill, the steeper the climb, the better the view from the finishing line. And it's by Paul Newman. And these two are very mysterious to me. This one says, never stop doing your best just because someone doesn't give you credit. Well, I first reread it like, never mind if the teacher gives you a bad rank, keep on doing it. That's not the message I want to hear. And this one reads, your best teacher is your last mistake. It has two different meanings. The first one is, you learn from your mistakes, and that's positive. Or it could be, hey, you listened to your teacher, and that was a big mistake. So, what is it?
Would you like the front like that?
No, I want people to see me.
It's okay.
Can you read that? So, well, maybe we can switch it up. So, well, the student's point of view was fine, so I know how they think a little bit more, but it doesn't give me the hints I need, the practical guide I need to motivate my students. So I went to a more serious, so to say, more adult side. Don't be worried, adult in the good sense. So I found this quote from Antoine de Saint-Exupéry. He's the author of the Little Prince. And this is very profound. It reads, if you want to build a ship, don't drum up people together to collect wood, and don't assign them tasks and work, but rather teach them to long for the endless immensity of the sea. Oh, that's profound. Yeah, no practical hints. But that's not too bad, right? So in the end, I had to do what I was supposed to do at the beginning and find some professional in psychology, cognitive psychology, or education, or pedagogy, or whatever. Then, of course, I resort to this conference by Peter Gerdenfors. Peter Gerdenfors is a very reputed Swedish philosopher and cognitive psychologist. And I don't know whether there are friends or enemies of Peter here, but I make sure that Peter was not here so that he cannot say, Paco, you got the message wrong. Right? So I can interpret what he said in that conference, which you can see in TEDx or in YouTube. And Peter makes the claim that there are 3 factors for motivation. After his studies, he says, and he also based himself in the work of Jerome Bruner, he said there are 3 factors for motivation. And the first one is what pulled me from my soul factor, curiosity. And we heard about this in yesterday's plenary lecture as well. So you have to go and search, stimulate the curiosity of the students. And this is important. It's one main factor, the first one, but it's not the single one. The second one is control. If the student gets lost, if he or she doesn't feel that he or she progresses in difficulty level, so he's mastering the subject, then they fell into despair. So you have somehow to provide them with the sense that they are little by little controlling what they're learning. That's the second factor. And the third factor is based in the fact that we humans are collaborative animals, beings, right? So one important part for motivating people, students, is to let them collaborate with others. I know this is not good for you, I know. But he stresses these 3 factors to stimulate motivation. And I'm going to base my work, my experience, and base my experience on this. Actually, Peter provides some examples of activities, human activities for youngsters that are very successful because they point at these 3 factors. And the first one is computer games, video games, which are very successful. It's a big industry, but they have been very good at doing this. So they stimulate your curiosity because in a game you can quest or follow an adventure or quest for something, some treasure. Or you might want to kill zombies. This, of course, stimulates everybody's curiosity. Or you might want to participate in a virtual world, whatever it is. But this is very attractive. They know how to attract the children's attention. The second thing, they make this progression level very clear. At the beginning, you start with a simple part of the game, so it's easy to complete the goals, but then you get to the next level, which is a little bit more difficult. And once you master this, and eventually you do it, then they take you to a higher level of difficulty. And this makes you feel, wow, good, because you are progressing. I mean, you know more than another colleague who's going to start from scratch. And the third thing is collaboration. Not only they can play through the internet, sometimes they gather together in a room, and one of the children play, and the other are sitting around them, giving advice or commenting the game. Another good example of this kind of motivation is in peer learning, which is things children learn by playing with their friends, like sports, not professional sport, or skateboarding, role games, or learn how to play guitar non-professionally in a group of friends. And I will also add, this is my 2 cents for Peter, the Scouts boys and Girl Scouts, how they learn, or learning languages in a foreign country. So again, Peter goes further in his thought and also elaborates this left-hand side part where he tells you what the teacher or how the teacher can do this from a metacognitive point of view. But I'm not a psychologist, so I'm going to concentrate on this part portion. Right? So remember, this is going to be present throughout my talk. If you want to motivate your student, here are my practical guides. Stimulate the curiosity of your students, provide them some level of control on how they progress, and help them, even ask them, force them to collaborate. That's the end of the first part of my talk. So now here comes to the second part. We come to the second part. And I'm going to tell you how I try to motivate mathematics students to improve their physics knowledge. And I do so by creating simulations. I'll tell you what this means. Well, this is the front page of our leaflet. So come to us and study mathematics. And the second page says why you should study mathematics. And the first lines that I translated that for you say, you will learn to recognize mathematics around. That's good. Second thing, you'll be able to use your mathematical knowledge in the definition of problems and solving them in many kind of concepts. But pay special attention to the third line, the third paragraph, which reads, you will be able to create, interpret, analyze, and validate mathematical models of simple real-life situations. Well, this is actually what mathematics are. They are a tool for these kind of things. Okay, so this is our promise. So how do we do that? What is our syllabus? What do we teach our students? And I have also translated our syllabus. Don't read it, because I will make it simple for you to grasp it. We have 4 years to do that, or 8 semesters, and I've only translated the names of the subjects in the 3 first years. Well, to make it, to say this, to describe this in a single sentence, I will make a comparison to something completely different. You know what this is? This is a cake, of course. It consists of a base of chocolate with several layers of different types of chocolate on it, with a cover of chocolate and some toppings made of chocolate. The name of the pie is Death by Chocolate. So what you're seeing here is Death by Mathematics. Well, I'm kind of joking, I shouldn't, because I'm the dean of the mathematical faculty. But these things are important. It's all the wisdom, mathematical wisdom throughout the century, linear. And we try to provide the basics of it to our students. But then you have to learn how to model real-life situations. How do you do that? Well, we have a little bit here of physics, 6 credits, semester of physics, which amounts to, for some mechanics, maybe dynamics, maybe rigid body motion, but not too much, simple things, and a little bit of weights. There's no room for more. And we have double 2 semesters of programming, Java maybe, and we also have well, how to use Maxima, which is similar to MATLAB, and Latin, of course, later. But finally, we have this subject here, which is called Modeling Laboratory. Hey, that's my subject. The one I chose, I always fight to get it. I don't have to fight very hard. But I love it. So in modeling laboratory, supposedly is where you have to fulfill your promise. We have to fulfill our promise. We need to learn them to construct models, evaluate them, run them, of simple real-life situations. And well, the goal of the subject is to teach students how to model a problem using mathematics, solving the problem even numerically if needed, and then check whether the model gives reasonable answers. My own approach, and I'm connecting to the first part of the talk, is to provide very little theory, not modeling, very little theory, no more theorems. That's enough. They have enough so far. And work through project-based learning, both individually and in groups, and using computer hands-on lectures. Because this is my opportunity to try to use interactive engagement techniques, which you all know probably, and combine math, science, and technology that has been proved that works for improving understanding, and to motivate them to learn some physics, more physics. So in this course, which is called Modeling Laboratory, I'm never forgetting that I need to motivate them to do physics because they are math majors. But I want them to learn some more physics. I did the following this year, 6 months ago. So I gave them individual assignment, one for this whole class, which is called Tarzan's Dilemma. Tarzan of the Apes, jungle, monkeys, right? Gorillas. I'll tell you what this is. So all the students had to do the same problem. And then I divided them into groups of 3, 4 people, and I tell them that was a more open problem. You've got to simulate, to model and simulate any amusement park ride of your choice. You choose. Well, we will talk about it to make sure that it's not too difficult or too easy, right? So this is what they came up with. First of all, I will tell you about the Tarzan's dilemma. I didn't invent it. This is a paper in the physics teacher that appeared in November last year. And it consists of a problem related to Tarzan. When I first studied that in my classroom, I was surprised what Tarzan brings you to mind. So if I ask you to get an image of Tarzan, so think about it. So what image comes to your mind? That's what I get, right, roughly. Well, so what do students get? It has nothing to do with physics, but I couldn't resist saying it. This is what they think when they think of Tarzan. All of them. They don't even know who Johnny Weissmuller is. Well, now, coming back to physics, the Tarzan's dilemma is the following. He's in some danger, and he's running to escape from it, and he comes to a river full with crocodiles. Oh, and the lions behind him, right? So, fortunately, there is a vine, I think this is the English word, hanging from a tree. So, well, he decides to grab the vine, running as fast as he can, balance, and then at some time release from the vine in order to jump across the river. So the dilemma is, at what angle should I release myself to make sure I cross the river so I reach the maximum distance? Well, we all know that Johnny Weissmuller was thinking about that every time he went to the vine. And that's a very nice problem. And the paper which I gave to my students described the solution partly analytically, and then you have to do a numerical computation to plot the solution. So it's not trivial. So I told him, I gave him the paper and said, you've got to create a simulation of this. Period. Just do it. And since Tarzan was interesting enough, because I need to switch to my tablet, well, tablet is the title of this talk, I will tell you the other two projects that I'm going to show, and then I'll move to the tablet, right? So I don't need to be switching forward back and forth. From this, remember the second assignment was a group assignment, and each of the groups had to decide on one amusement park ride. And one of the groups decided to simulate this. This is a teacup ride. Well, it has different names in different places. I think there's one in Disneyland. What it consists, I will tell you what it consists of, but it's basically rotating platforms. And then the teacups are free to rotate around their own center. But the platforms in which they sit, they rotate. And the third example I'm going to show you today is this one. Now I think we should turn off the lights. Can we please turn off the lights? And the third example, this is another group word, is this one. This is Terra Mythica, is an amusement park which is 90 kilometers from home. And this is a wild ride. It consists of, these are people right here, you see? You can see that they move their legs. So they're sitting with their legs on the air, and they are, for some reason, they pay for it. So the cylinder in which they sit rotates around its center, and then the big swing, the big axis swings very slowly at the beginning, but wildly at the end, until it reaches something like 120 degrees up. Well, they chose that right. So they had to program this for me. And there are a few physics things I need to learn to do that. Oh wow. So it's becoming dangerous. What if some of them loses a shoe or a cell phone, whatever? Remember that question. So what I'm going to do now is I'm going to switch to the tablet and show you what they did. Well, to be completely honest to you, I have polished their solution, right? But what you're going to see is looks very much like what they did, including the physics. And I switched I want to connect to the third part of the talk, when I will finally talk about how to do this, how and why to run it on tablet. So this is my tablet, and our team has created this. Well, one of the problems you cannot see when I'm pointing at. So I'm pointing at the second icon there, the one with a gyroscope on it that reads free. I click on it, and here is my personal library of some simulations that we have created. And I have included in this collection these three that you see here. You see torsion, you see the T-tabs, and you see the syncope, the balancing attraction. So when I click on the torson's dilemma, well, I get a little bit of narrative, and then I go here, and here is the simulation that they created for me, right? So I can choose that torsion. Here you can see torsion fighting the leopard, and then at some time he will get rid of it. So I will tell it that I will solve the dilemma for him. And I would say, whenever you reach 40 degrees, you release from the vine. You can see the vine hanging there. And this is what happens. So you click on it, person runs. Okay? And there it is, and he did it. And he's so proud of himself that he had his typical, oh. Well, simple as it looks, that was done by students, right? Individual, by all of their students. I chose the best solution, right? And it combines some very nice physics problems. First is simple, is uniform motion at the beginning. Then you have a swing part. I'll leave that for the last one. And then you have free fall. How would you model the middle part? Well, you need to compute the angular velocity, because it's an angular motion, right? A circular motion. It's a pendulum. But how would you model it? So the students started modeling it using a simple pendulum, which means torsion is a mass point. I can accept that. It's a big mass point. And the rod is a massless rod. That's a simple pendulum, right? So and they did that. That was the first entry level, and they were for it, and they had to review all the physics knowledge, and they need to learn how to preserve linear momentum in order to compute the angular velocity at the moment of when torsion grabs the rope. But what happens when torsion releases the rope to the rope? It is massless. So they had to go and progress to the next level and say, you need to implement a physical pendulum. And to compute the physical pendulum, because it's not a single body, it's two bodies, torsion and rope, you need to compute the center of masses. And then you need to go to a number of things. And when they did, I do that just for fun. Someone decided to let torsion, I will rerun again, to let torsion release at 60 degrees. So maybe he reaches further. And when they run that, what happens is this. And they say, oh my teacher, the simulation is broken. It doesn't do what it's supposed to do. That never releases it. In their solution, that some will remain hanging from the rope, right? I implemented that, and when he comes back, he falls into the original point. So the simulation is broken because it doesn't release it from the rope. Well, of course, at that speed, it doesn't reach the maximum angle. There are a number of physical things you can learn about it. But remember, I told them to solve torsion dilemma. So another thing they can do now, and I asked them to do that, is to scan the solution, simulate several times faster from the current, from 20 degrees to 60 degrees with an increment of 1, and do that several times. Okay. So torsion is doing the experiment over and over and over again. And they're plotting the solution right here. And this graph they get matches exactly or closely the analytical solution that appears in the paper, in the physics teacher. So as you can see, the solution is somewhere 30 degrees, but it depends on the initial velocity, of course. So that was the way I tried to motivate my students to learn somewhat, to review the physics they learned. This was an individual